Hello, in this video we're going to look at instantaneous velocity and speed. The instantaneous velocity and speed are more typically what you mean when you say velocity or speed. It's the value of these things right now or at some particular time, whereas the averages that we talked about in an earlier video are over a longer period of time, over minutes or hours or days or even without limit. So for instantaneous velocity, we're going to again have a vector like we did before. So the velocity is going to be a limit as the interval of time shrinks down to an instant. That's what makes it the instantaneous velocity. So we'll take the displacement over a very, very short period of time. And you may have seen something like this before. If we have a limit of two deltas, that's actually going to be a derivative. So it's the derivative of the velocity, the velocity is the derivative of the displacement with respect to time. So that'll be one of our definitions. And we'll compare that with speed. Speed is just the magnitude of the velocity. So that's an easy one. In other words, speed leaves out the direction part, whereas velocity includes both that magnitude and the direction. So if we make a sketch here, we'll try and draw the same shape that we had last time. So we have a time axis and a position axis. And we had something that was negative for a while and came back up. At any given moment on there, we're going to have at each point we have a different instantaneous velocity, which is the derivative, and the derivative on a graph is the slope. So we have different slopes, different tangent lines at different points here, corresponding to the fact that the instantaneous speed has different values. Over here, the instantaneous speed is negative. Right here at the bottom it's 0, and here it's positive. Here it's even more positive. And so that's handy. So that shows us, instead of just as an overall gross average, what it is from moment to moment. Now something else I want to point out. Since velocity is the derivative of displacement with respect to time, and we're going to work in one dimension here, so I'm going to leave off the vector signs, we could rewrite this. We can say that dx is equal to velocity times dt. And what I've set up here basically is a solution to a differential equation. This is a differential equation, a very simple one, called a first order separable equation. Separable because I can separate these two terms to either side. And the way you solve these sorts of things is you integrate. So we just integrate both sides of the equation. And yes, you can actually do that. So on the left-hand side, we're going to get x. And on the right-hand side, well, we'll just leave that as a derivative or as an integral, v dt. And we're also going to have some unknown constant because of this integral with x. Okay? We'll see exactly what this constant is in a little bit, but it turns out that this unknown constant is the initial position, is x initial. So let's make a little sketch here on this next slide. So we'll do a coordinate system x and t again. So let's see, try and leave room for two of these graphs. So we'll have t and x. Okay, and maybe even, it's not going to let me get away with that. All right, see if I can copy and paste or if this is a disaster. Let's see. All right, that worked. And we want, instead of that, to be a v. All right, so two graphs that look just about the same, one plotting displacement, the other plotting velocity. The relationship between these two graphs is to go from the x to the v. We're going to say that velocity as a function of time is equal to the time derivative of x. In other words, we're going to look at the slope. And we can go back again. So we can go from the velocity graph up to the x graph using x as a function of time is equal to an integral from 0 to t of v of t dt plus whatever our x initial is. We'll say plus 0. So we'll start our graph here at 0. And let's say it looks like a straight line that suddenly changes its slope at some point. Has a little kink in it. Okay. So what would it look like if we plotted the slope of this thing? Well, all the way until we get to this point here, we have a slope that's constant. So that would just be a horizontal line. And then after that, we still have a constant, but it's a different, larger constant slope. Okay, so our graph of our velocity would have sort of a staircase look to it. And so that would be going from the position graph to the velocity graph. We can also go the other way. That's a little bit harder to visualize. But imagine that we start integrating. So we start integrating at 0 up to t. When you integrate, what you're doing is you're finding area. So we integrate, say initially we start with no area, so our plot would be here, and then we start integrating, so calculating area. Let's say we go up to here. Okay, that's a number. That would be here, and we go a little bit further, and it's here, and we go a little bit further, and it's here. And now we're starting to add increasing area, so we start to climb our graph faster. Keep integrating, and so on. So you can go the other way. It's a little bit harder to visualize than going from slope down to applying the slope of a function, but we can in fact go either direction. All right, so we'll talk a little bit more about these integrals or antiderivatives in a future video. Until then,